of today. This will be Yoram Last from the Hebrew University, and he'll talk to us about level spacings for Jacobi operators.
Well, thank you, and I would like to first thank the organizers for the invitation to speak here at this very interesting conference. And what I will talk about are the simplest type of Schrödinger operators. So these are just three diagonal matrices on L2 of n, Laplacian plus potential on a half line sort of. And everything that I will talk about and all the results that I will mention actually have analogs for more general three diagonal operators, but it's just a lot simpler to deal with just one sequence rather than two, when instead of the ones you put some ANs which are different off-diagonal elements. So to simplify the presentation, I will just talk about these models. And so for such a matrix, there is a unique spectral measure, a canonical sort of spectral measure, which is just a spectral measure associated with a vector that is a sort of delta function at the origin. And I have somehow in the back of my mind that this operator is actually going into a time-dependent Schrödinger equation, and there is an underlying evolution in time of initial vectors given by this solution of the time-dependent Schrödinger equation, where the vector at time t is e to the minus iht multiplying the vector at time 0. Now, such an operator, there's an associated generalized eigenvalue equation given by this one, and because there is a kind of, if you move say Vn to the other and psi n minus 1 to the other side, you can see that psi n plus 1 is determined, of course, by psi n minus 1 and psi n. So if you know psi at any 2 points, you know also for larger values of n. And it's very standard to write this generalized eigenvalue equation in matrix form like this, and then the vector at n plus 1 and n is determined by the solution at n and n minus 1 and so on. And by taking a product of these matrices, you can then get the solution at any consecutive 2 points n plus 1 and n from the initial value at 1 and 0. And phi n will be my notation for this full transfer matrix, which is the product of the one-step transfer matrices. Now, of course, it's also interesting to note that when you fix psi at 0 to be 0 and psi at 1 to be at 1, then of course the psi n's are in fact polynomials in the energy E, the sort of generalized eigenvalue parameter, and in fact it is precisely a polynomial of degree n minus 1 for psi n. And in fact the various psi n's from 1 to infinity are exactly the so-called orthonormal polynomials with respect to the spectral measure. Now, I'm going to be interested mainly in absolutely continuous spectrum of such operators. And absolutely continuous spectrum is completely determined by its essential support. The essential support is which can be a somewhat smaller set, is actually an equivalence class up to sets of 0 Lebesgue measure that can be taken to be up to, again, sets of zero Lebesgue measures, which are not significant. It can be taken as a set of energies where the spectral measure has a finite positive derivative, or equivalently, one can look at the imaginary part of this diagonal resolvent matrix element and look at the set of energies where it has finite positive limit when one takes the imaginary part to 0. And the AC spectrum itself, which is a closed set, is then obtained as the essential closure of this essential support by this formula here. Now, it's a wisdom that sort of goes many ways back, that absolutely continuous spectrum has roughly at least something to do with generalized eigenfunctions of this equation, namely solutions of this generalized eigenvalue problem being bounded. And for many, many years, it was actually believed that the following is true, that the essential support of the absolutely continuous spectrum is simply the same as the set of energies for which the transfer matrices are bounded. Well, when the norms of transfer matrices are bounded, that of course means that any solution is bounded. So it's natural to look at the norms. Now, I don't know why this has been called the Schrödinger conjecture, because I think in the works of Schrödinger he somehow assumed that he can just look at the set of energies where you have bounded eigenfunctions and sort of consider this as sort of eigenvalues in cases where you don't have eigenvalues for the supposedly continuum spectrum or whatever. But this name was actually given by some people in the 1980s somehow, and it was considered a big open problem for a long time. The surprise in a paper that just recently appeared in the Journal of the AMS of Arthur Avila is that this is in fact false. And it actually would have made a lot of things very nice and simple if it was true, and it was believed for a long time, but this is false. Still, somehow, it is false only by an epsilon. So the results that are sort of known up to date, it is actually a question how far things can be taken further, include the following. So first of all, there is a theorem that Barry Simon and I obtained that was already more than 16 years ago, that says the following. So first of all, if you look at this Cesaro average of the norms of transfer matrices, and I now note that there is actually a mistake here. There should be a square here. There is a typo. There should be a square here, like in the lower formula. But up to this typo, if you look at this Cesaro average, then in fact having a finite lim in for this completely characterizes the essential support of the AC spectrum, so that at least on the AC spectrum the transfer matrices cannot grow. And moreover, it's not very meaningful to say Lebesgue almost every for something in the essential support, since it is itself defined only up to sets of Lebesgue measure 0. But in any event, on the essential support of the AC spectrum, also the lim sup of something which is pretty close to this, you just need to divide here by another log of n squared, must be finite. That means that the limit of the Cesaro average must be finite, and it is actually infinite outside the essential support of the essential spectrum, and but we don't know that it's bounded, but it cannot grow more than logarithmically for ends where it is large. I should also note that, of course, the outside the essential support of the AC spectrum, of course, this type of Cesaro average, of course, don't need to be a square here, is actually infinite. And moreover, for example, if E is an eigenvalue, then this sum needs to be finite, which means that these norms need to grow even at a sufficient rate to make this finite. Now, another thing which is still a very recent result, the paper is now in the process of being written, is that if you fix any interval, well, I take an open interval, then if you look at integrating over this interval 1 over the square of the norm of the transfer matrix, then this in fact goes to 0 and then goes to infinity if and only if there is no AC spectrum in this interval. Now, so this is now a sort of a different kind of average. In a sense, this was looking at the fixed energy, but somehow averaging over the ends to get a result which is fairly close to saying that these norms want to be bounded. It actually works nicer if you're averaging over energies in an interval, because here there is a strict result about either there is AC spectrum or not, and if there is, then this thing cannot go to 0. So that means that in an average sense, these norms are small, on at least some of the energies, of course. Now, our interest in this actually comes, and also the relevance of this to transport in the system, comes because there are various formulas, Landauer-Buttiker formula and something called the Thouless conductance. There are various formulas that physicists came up with in the 1970s, and that actually gives the conductance of a finite segment of such a system, if you think of it as a one-dimensional conductor between two electrodes. Now, when you describe such a system, actually, although the physicists actually tend to consider it always taking the energy to be some fixed energy, in a real physical problem, you actually have an interval because you have a voltage difference between the two sides to make a current, and you look at the current, which is actually going to flow inside, which is connected with this energy interval. So it's actually natural to look to associate conductance with an energy interval, and what Yaktik and Pilet were doing is actually to derive and justify rigorously these formula of that were derived very heuristically by physicists in the 1970s. So now, of course, the problem is a bit tricky when you want to define conductance, because it actually depends on the electrode. So it's not like there is really a very unique notion of conductance that depends only on the wire, but it's also a question of how you connect it and so on. But in any event, the point is that all these various a priori perhaps different quantities, the Thouless conductance, the Landauer-Buttiker conductance, they can all be shown to be equivalent up to in units where all constants are 1. so that you don't care about constants. They are all equivalent, and in particularly one goes to 0 if and only if the other goes to 0, and they are all go to 0 if and only if this integral goes to 0. So the vanishing of this integral is equivalent to the vanishing of the conductance under any technical definition that you want to take of it. And actually this result was really motivated quite strongly by the disproof of the Landauer of the Schrödinger conjecture by Avila, because of course if the Schrödinger conjecture were true, then at least one direction of this would be immediate from it, but it isn't. But it's not really, its failure is not really relevant, for example, for the purpose of conductance, because then you only care about integrating on small maybe, but still energy intervals. And once you do that, it is really effectively like AC spectrum means that these norms don't grow. Okay, so this is what we know. It's still not clear what is the most optimal or closest thing to the Schrödinger conjecture that one can get in general. But this is an interesting question given that the strict Schrödinger conjecture isn't true. Anyway, this was all some kind of introduction to the issue of mainly connection between AC spectrum and non-growth of the norms of the transfer matrices. And now I'm going to be looking at what is really the topic of this talk. And for this, I'm going to basically cut a finite piece of my operator. So I'm going to look at cutouts, which are just 3 diagonal n by n matrices, like this one. Now, once I do that, this matrix has simple eigenvalues, n eigenvalues. And it's intriguing that these eigenvalues happen to be exactly the d rows of the n plus 1 orthogonal polynomial. So talking about these levels and what they do, these eigenvalues, is also the same as talking about zeros of orthogonal polynomials. And what the general sort of question is, how is the behavior of these eigenvalues connected with other things? And of course, I'm mainly looking at the limit as n goes to infinity, and I want to ask how the behavior, whatever it means now, how the behavior is connected to, say, the dynamics or the spectral properties or the conductance or any other things that I may care about concerning this system to begin with. So the sort of first order quantity that comes up in the context of looking at the eigenvalues is the density of states. So the density of states is basically a measure that is looking at how many eigenvalues fall inside the set S. This is the sort of density of states, which is of course a singular measure for finite n. Now, if it happens to weakly converge to a limiting measure, then we can say that there is an existing limiting density of states measure, and this is what I'm going to mainly assume throughout the rest of the talk, although there are problems where the limit doesn't exist. So this limiting knee is the density of states measure, and if it has an absolutely continuous piece, so there are significantly many e's for which it has density, namely a derivative with respect to Lebesgue measure, then this density is the density of states. And of course, if is absolutely continuous, then the density of states measure is just given by the density of states multiplying the Lebesgue measure. Now, I don't know who is the one that had this horrible idea of calling a measure density, because it leads to virtually impossible terminologies, because, yeah, well, so the density of states measure is the density of states.
The IDS. Yoram, why don't you call the DRS measure the IDS? Why don't you call it the IDS? Integrated density of states. That's the density of states measure.
No, that's the distribution function of the density.
That's the distribution function.
Anyway, this is life. So, but now, but the existence of the density of states and the fact that in many problems, and that's what I'm going to care about here, you have at least, if you look say at an interval or any other measurable set, there will be a limit to the density of eigenvalues there. That's sort of the first order problem. The second order, and then you can ask higher order problem, sort of, and you can wonder about, given that you already have, say, something like on the order of n eigenvalues, because, right, if you have a positive density of states in some interval, then as the n grows, the number of eigenvalues inside that interval will grow like n. But the question is how they are distributed there. And that is, of course, the desire to look at these things is impacted by questions by works, for example, in randometric theory, where people all the time look at these distributions of eigenvalues of random matrices, and in particular how the different spacings between the eigenvalues behave, and so on. And actually, even before randometric theory was even born, people looked at these questions in the context of just asking how do the zeros of orthogonal polynomials look like. And the first work I know on this is actually by Erdos and Turan from the 1940s. They published a very nice paper in the Annals of Math about controlling these spacings for orthogonal polynomials, which is completely relevant. But anyway, so this is now what I'm going to wonder about, and in particular about the strict spacing between near eigenvalues. Do we have level repulsion or not in various situations, and so on. So a very general, sort of universal general bounds were obtained by Simon and me in a paper that appeared in 2008. So we've shown in particular the following two things, right? So here you have you fix some energy, and basically you are looking at the eigenvalues that are nearby. So one thing that we've shown is that there is this strict bound on the spacing of the eigenvalues just above and just below these energies in terms of the sum of the norms of these transform matrices. So that means that now if you're in a situation where these transform matrices are essentially bounded, of course these norms cannot be less than 1. So bounded means they are roughly 1. So you sum from 1 to n, you get something which is n here. So basically, in this situation, which intuitively is associated with absolutely continuous spectrum, basically you have this kind of repulsion that the eigenvalues cannot be closer than 1 over n roughly to each other. There is also an upper bound that again, now this is formulated somewhat differently because we are looking at what is happening in an interval, But then if in that interval you have some bound on this time the n+1 transfer matrix such that it is not large, then it's actually tell you that no eigenvalues can be farther than again something which is 1 over the n, or well, if the transfer matrix is large, then it's something large divided by n, but it is still the order of the magnitude of the transfer matrix divided by n. So this means that, for example, in situations like the free Laplacian periodic problems and so on, where we know that the transfer matrices behave very nicely and they basically they are bounded and don't grow and so on, then we know that in fact in all those situations that are associated with the nicest types of AC spectrum, there is this sort of order 1 over n spacings between the eigenvalues. Now, another thing that I want to remark in this context is that if you are in a situation where the transfer matrices do grow, then of course you still have this kind of level repulsion about eigenvalues cannot be too small, but the distance between near eigenvalues cannot be too small, but the not too small, for example, if these scales like some power law in L, then the not too small will still be can be a lot smaller than 1 over n, and similarly, if this is say something which is not order 1 but say order of n to some positive power, then you also get an effective bound on how far apart the eigenvalues can be, but it will no longer be something which is like 1 over n. So there is this kind of freedom as soon as the norms of the transfer matrices are not strictly bounded. And the point is that whatever freedom you have, it is already, you lose any control about you lose any kind of constraint about what the finite level spacing, limiting level spacing distribution may be, okay? Because if you have bounded eigenfunctions and bounded the norms of transfer matrices, and so everything is sort of very constrained to have spacings of 1 over n. But suppose that these norms are grow like L log L, grow even logarithmically, then I don't see, from these bounds at least, there is nothing to constrain the eigenvalues from ultimately achieving, say, a Poisson type distribution at the limit, okay? Now, I don't know if that can happen or not. What I do know is that these growth rates of norms of transfer matrices, well, they're of course connected, as I pointed out, with, for example, how conductance in cases where it does vanish, the rate at which it vanishes. It can also be, these growth rates can be connected with transport. For example, if you just look at this time evolution and ask how an initially localized wave packet will spread with time. So we know how to somehow combine all these things together, norms of rates of growth of solutions, or norms of transfer matrices, and dynamics and conductance and spectral properties, and certain power law growth rates of norms of transfer matrices can be associated, for example, with singular continuous spectrum that sometimes have appropriate dimensionality properties like singular continuous spectrum that consist of spectral measures that don't give way to sets of too small house of dimension but are supported on sets of house of dimension that is strictly less than 1 and so on. So all these things are connected together. Now there is something floating in the air and it certainly is a central motivation behind the interest of physicists in random matrices, and also I presume the interest of some of the people that have been looking at eigenvalue distributions for this type of problems. There is some expectancy that the limiting distribution of eigenvalues will actually say something about the physics of the system. I've seen absolutely no evidence of that. So it is known, for example, since the 1980s, that if you take a random potential, sort of one-dimensional Anderson model, it basically results going back to Molchanov, although it worked on continuous models, but never mind, that in the 1980s, that you get Poisson statistics for the levels, and this is supposed to be somehow associated with really having localization and so on. I'm not familiar with anything that is preventing even a singular continuous spectrum of dimensionality 1, which means a spectral measure that doesn't give way to sets of house of dimension less than 1, which is in a sense very close to being absolutely continuous. I see nothing that should prevent such a spectral measure from being associated with, say, Poisson level distributions, because as soon as there is no control that is somehow associated with strictly bounded norms of strictly bounded generalized eigenfunctions, which really lock you into 1/n spacings, I mean, even if you just have a kind of a log n type deviation, in the limit there is no restriction on getting any kind of distribution. So this is sort of a question whether
I'm not sure what you're saying. I mean, all you're saying is that as long as there's no constant bound here, you can get distribution with non-compact support. It could be Poisson, it could be random matrix theory, it can be anything, right?
it can be anything.
So,
It can be anything.
what is your
What I'm saying is that I don't know, but it can be anything. But for example, suppose that you have a problem where the limiting distribution is Poisson, okay, but this thing is growing only logarithmically, say. Then the limiting distribution will be Poisson and maybe indistinguishable from, say, a distribution you get for an Anderson model. But the rate of convergence is what you will read here, because for any n, the eigenvalues cannot be closer than 1/n log n. But the point is that this extra log there means that in the limit anything can happen, but it does control the rate of convergence. So it is not clear to me that the limit is saying anything. It's possible that just the rate of convergence is the central question. I don't know. I'm just saying that one of the things that I find interesting in this whole set of problems, of course, because if you have an operator and you look at the full family of eigenvalues that you get out of all these cutouts, this actually, of course, holds everything, all the information about the system, and it's actually a lot more spectral information than just looking at the spectral measure. But it's not completely clear what you can read from it and how it is connected to other things. Anyway, for the rest, but this is now, I was mainly mentioning things that I just don't know. The somehow regime where everything is nice is the regime of AC spectrum, when things do fall under much more control. And in this context, actually, I believe up to now, all problems with AC spectrum where one could actually say something about the spacing of the levels, one observes a phenomena that has become known as clock behavior, which means you don't only have order 1 over n spacings between the eigenvalues, but in fact you have strict equal spacings, in a sense, between neighboring pairs of eigenvalues. So if you just look again at this labeling of the eigenvalues, there are various definitions that one can give. So what Barry and I called quasi-clock behavior is just saying that, right, for each fixed j, that you take here, the spacing between the pair of eigenvalues will, as n goes to infinity, be the same as the spacing between the two ones at the focal point. So, and that means that you really get this kind of picture. Now, the name clock spacing comes from the fact that Barry actually first looked at this for orthogonal polynomials on the unit circles, and then the zeros fall on the circle, and then you get these equal spacings on the circle, and it just looks like a clock. So that's where the name comes from. But on the line, it just looks like a ruler, so maybe it would have been more natural to call it ruler behavior. But in any event, so quasi-clock just means that in the limit, all the eigenvalues around a certain energies have equal spacing. Now, strong clock, and this is something that can be observed and can exist even without having any kind of density of states existing. Now, what we call strong clock behavior is basically the same kind of behavior, but for cases where the density of states exists and the spacing is really the right one that corresponds to the density of states. And I should just point out that it is actually natural also to consider not just the spacings of the eigenvalues, but the spectral weights of the eigenvectors. Basically, if you look at these psi-Ls, then for each eigenvalue, this is actually just the eigenvector of the corresponding matrix. So requiring this limit to be 1 is basically the same as requiring that, right? I mean, these finite matrices also have spectral measures for the vector, which is delta 1, which is delta function at the origin, and 1 over the norms of 1 over this sum is basically the spectral weight there. So in virtually all problems that we know, not only the eigenvalues are of equal weight, of equal spacings, but also the spectral weight are equal, sort of order 1 over n at the neighbor. So this is also a characterization of all these problems. Now, it has actually been conjectured by Avila and Simon and me that at least quasi-clock behavior must hold almost everywhere on the essential support of the AC spectrum. Certainly in all problems with AC spectrum up to now, where we know what the spacing of the eigenvalues are, then this is what we see. We see basically this clock type behavior. And in fact, what one sees in, I think, all of these examples, right, where the first and most natural one is, of course, the free Laplacian, but also any periodic problem is exhibiting this behavior. And what you actually see is not only clock spacing, but a stronger behavior that people call universality. So for this, I'm going to look at the Christoffel-Darboux kernel, which is just this sum here, which is basically kind of like a scalar product over a scale of n of these generalized eigenfunctions, but at different energies. Now, of course, different zeros correspond to or different eigenvalues of these matrices correspond to eigenvectors which are orthogonal. So the points where these different eigenvalues corresponds to exactly zeros of this Christoffel-Darboux kernel. And the phenomenon known as Bach universality is saying that uniformly for A, B in compact subsets, what you get is this type of convergence of the Christoffel-Darboux kernel at E naught plus A over n and to E naught plus B over n divided by the diagonal sort of Christoffel-Darboux kernel that converges to this sign pi. Of course, here we assume the density of states exists, and this sign just divided by the B minus A. And it's a basic theorem that coming again from the fact that basically the eigenvalues are in fact the zeros of that Christoffel-Darboux kernel. So the zeros are the zeros of this sign. That if you have Bach universality, that implies the full clock behavior, which means not only what we've called at some point strong clock behavior for the eigenvalues, but in fact also the spectral weights are sort of equal for neighboring eigenvalues. Now, as this conjecture suggests, generally this phenomena of universality and in particular the resulting, if you like, a strict clock behavior of the eigenvalues is thought to be something that is sort of associated with AC spectrum. And in a sense, the problem is, the big problem in a sense, from my perspective here, is somehow showing what we believe, that there must always be at least some sort of clock behavior or universality or whatever, almost surely on the absolutely continuous spectrum. It somehow seems natural that if you have no AC spectrum, then you don't have this clock behavior. But it was a big surprise for me, at least several years ago, when Jonathan Breuer actually found this phenomenon of strict Bach universality to occur also for an operator where you have no absolutely continuous spectrum, but rather purely singular continuous spectrum. So,
what is that operator?
What is that operator? Well, the operator is basically some kind of a sparse Schrödinger operator, where the potential is basically well, he actually worked with off diagonals, but never mind. But it's a sparse operator where it is just a free Laplacian most of the time, and then there are some bumps, but these bumps are sufficient. If you want a Pearson type kind of, yeah, it's quite similar to a Pearson type problem. Yes. Okay, so okay, this is life. So universality can occur even without AC spectrum. but when does it occur? So it turns out that another natural feature of many systems that has been useful in the study of looking for this universality in various models is well, these are not notions that anyone has written in any paper, partly because my co-authors didn't thought that calling things nice convergence and so on is something that it would be a good idea to define in any sense, but for the sake of this talk, I will say that there is nice convergence of the CD kernel if this limit of 1 over n, the diagonal CD kernel, converges in a pointwise sense exactly to the derivative dνt dμ. Dμ is the spectral measure, dν is the density of states, which I, as I pointed out, assume to exist here. Now, what I should point out that it is a completely general fact whenever the density of states exists. If you multiply both sides here by dμ, then in the sense of weak convergence, 1 over n kn multiplying dμ weakly converges to the density of states dν. So this is a completely general fact. So what this means is that what is generally occurs as a weak limit actually takes place as a pointwise limit with this quantity pointwisely converging to the value of this derivative. Now, so if you have this nice convergence of the CD kernel, you can also now ask, and this is connected now also with the question of how stable this universality phenomena may or may not be. So if you have this nice convergence, you can also ask whether it will be stable or not when you make small perturbations of your operators. And the sort of simplest perturbation to think of is a rank 1, something which is basically just the same as changing the boundary value of the problem. Namely, if you add lambda to V1 in this matrix, then this is basically the same as adding a rank 1 perturbation of this form. It's just adding a lambda to the value of, to the diagonal element at the uppermost corner, to the potential at point 1. And so this change of boundary value, and one of the things that, for example, distinguishes AC spectrum from singular spectrum is that AC spectrum is stable under such rank 1 perturbations, whereas it is well known that singular spectrum in fact must move in the sense that when you continuously change such a lambda, then actually the actual support of the singular measure, eigenvalues, for example, in the case of point spectrum, it actually moves with lambda all the time, so that from different lambdas you get different supports, and moreover, point spectrum can become singular continuous and vice versa under such perturbations. But stability under them is a characterization of absolutely continuous spectrum. And since universality is supposed to be associated with AC spectrum, it seems kind of natural to wonder whether or not or when it is stable under such perturbation. Now, it's sort of elementary exercise to see that basically comes from the fact that it takes 3 points, right, to determine a parabola. That if you have if something like that, if this convergence is occurs for 3 different values of lambda, then it must already occurs for all values of lambda. But so if there is this stability, then I will say that there is not just nice convergence, but in fact stable nice convergence. Now these questions have been useful in a joint work of Artur Avila and Barry Simon and me, where we actually tried to see whether this clock spacing universality occurs or not for ergodic Schrödinger operators. And so, first of all, one thing that we've shown is that once you're on the AC spectrum, and this is a deterministic result, it has nothing to do with ergodic or not, then for almost every energy in the essential support of the AC spectrum, in fact, stable nice convergence of the CD kernel implies back universality. And then we essentially use that by effectively showing stable nice convergence of the CD kernel for ergodic operators with AC spectrum, that in fact for ergodic Jacobi matrices there is this stable nice convergence, and therefore back universality for almost every energy in the essential support of the AC spectrum. So basically what we roughly conjectured to occur for any operator, we were able to establish for ergodic operators, but it's not clear what is happening in general. But more recently, Jonathan Breuer and Barry Simon and I, we looked more closely at the question of, okay, suppose you know some problem has universality, what can you say about its stability under small perturbations? And we have proven the following theorem. So that for almost every energy in the essential support of the AC spectrum of any such operator, if you have nice convergence of the CD kernel and you have universality, then this nice convergence is also stable. And that means that this whole universality is becoming stable, in particular under rank 1 perturbations at the origin. But not only that, then you can actually extend it and get the stability of this universality behavior. For example, if you perturb the potential by adding to it any other potential W, which is in L1, and also you get almost sure preservation of the universality if you add a random perturbation made of independent random variables with zero mean, as long as you have this kind of L2 type conditions. So think of a problems where you know that the transfer matrices of the unperturbed problem are in fact bounded like a periodic problem. Then if the sum of the expectations of the squares of the random variables is finite, which means that that kind of what you might naturally call L2 random variables, random perturbation, then such a perturbation will also preserve the universality. So now you can, for example, take any kind of, you can take a periodic problem, or in fact any kind of ergodic problem with AC spectrum, and once you add to it, say, such an L1 potential, you still get a problem where you know you have universality. So this actually covers a lot of things that previously were done as a separate example. For example, just taking the Laplacian plus some potential that is decaying at an L1 rate and showing that it has clock behavior, which is something, for example, that was done by Barry Simon in some paper close to a decade ago. But anyway, so this is what is known up to now, to me at least. And a final question I should point out, again, something that is not clear to me. We are looking at this clock and we're looking at this universality because that's what people have been looking at, also for various other problems. Again, it is not clear to me at all that this, what we're looking at here, is really a natural question. And that is for the following reason. When you ask, for example, about this, well, you can also look at the clock type of properties, but when you ask about this behavior, you're fixing, right, the scale of energies where you're asking for this convergence to occur within is shrinking like 1 over n. And you're looking for just this pointwise limit for basically an energy scales that are shrinking like 1 over n. That means that in the limit, they don't, the spectral weight of the total eigenvalues, that number of all the eigenvalues that play a role here, the spectral weight is going to 0. Now, in all the, well, I don't know all, but in most examples, if you have a periodic operator, for example, then actually you know something a lot stronger than that, because the actual clock behavior or universality behavior that you get is such that you can basically more or less fix the microscopic energy window and take n to infinity, and the number of eigenvalues that will have the X-well spacing will grow like n as n goes to infinity. And here you're basically fixing an energy window that shrinks like 1 over n. This is somehow the type of limit that people have been looking at, and it is actually but then the result of it, of course, makes things much easier to prove than otherwise. But to the extent that, say, this phenomenon of universality is saying something about the physics of the system, I would actually, I very much doubt if this is saying something. I would expect that I would need to look at maybe something that is an energy window that is shrinking, but maybe shrinking at arbitrarily slow rate, not something that is shrinking like 1 over n. So I've been looking at these various problems, but the sort of standard questions that have been the game, it's not clear to me that all the questions that have been looked at in this context are in fact the natural questions. So it's not clear to me that one should actually look at these limits. It's not clear to me, like I said before, that the limiting distributions that a lot of people have been very interested in is really saying anything about the physical properties of the system, or maybe whatever the limiting distribution is, it may be a lot more important what is the rate of convergence to it rather than what the limit is, and so on. So for me, this whole thing is more puzzling than anything else, and thank you very much for listening.
Questions or comments? Well, I have a comment to your puzzlement. So in the quantum chaos subject, it's well understood that you restrict to the local scaling 1 over n precisely to see universality, to kill fine details of the system and just see different universality classes. But if you go to longer range correlation, what you want to do, you start recovering details of the system. So I can give you some literature on this. So this is a well understood phenomenon once you look at deterministic systems, as well as, for instance, zeros of the Riemann zeta function, where it's known that if you look at short range scaling, you see random matrix statistics. If you look at longer range scalings, you start seeing prime numbers appear in the long range scaling.
All right, but here you're talking about a specific type of convergence. So, of course, if you somehow look at information that looks at all the eigenvalues, then you know everything about the system. But the point is that when you look at a limit like this, and you just fix your energy, and so there is nothing, I mean, maybe there is something, but which I don't know, but there is nothing that I know of, for example, that will prevent this thing from converging very nicely to this. But as soon as I will actually take a larger energy window, then this will not happen. So the fact that I have a pointwise limit at even almost every energy doesn't necessarily mean that I will have the nice behavior over large scales.
Oh, exactly.
And therefore, again, so it's not clear to me that this is really saying something important. Oh,
well, about that specific question, I don't know. But as I said, different scaling limits give you different answers. Short-range scaling limits give you answers about universality. Long-range scaling limits recover details of the system.
And in general, if you throw n independent random variables and you want to see Poissonian statistics, you need 1 over n intervals. Otherwise, you don't see it. It's a very natural scaling for that, to see Poissonian statistics. So, why?
Yes, correct. Any other questions, remarks? Well, it's been a long day. Thank you very much for your talk.